I'm afraid this is a somewhat modified version of a talk I gave last year at the memorial meeting for Quillen at MIT. It's not exactly a talk about Quillen's work, but it's a talk about thoughts aroused in me by preparing a talk about Quillen's work. And it's certainly not going to have any new theorems. I'm just going to try to present a kind of way of looking at things. So the first generalized cohomology theory to be invented was the K-theory of Atiyah and Hirzebruch at the beginning of the 60s. So they started off with a compact space X. Does this work, by the way? Am I audible?
Yes.
They started off with a compact space, and they defined a group K naught of X made out of the finite dimensional complex vector bundles on X. So you take the isomorphism classes of complex vector bundles, they form a semigroup under direct sum. You formally adjoin negative elements, and that gives you an abelian group K naught of X. And the point is that they were then able to make this into a cohomology theory by defining other groups. First of all, they defined negative ones, roughly speaking, by applying the same functor to the I-fold suspension of X. And then they used the Bott periodicity theorem to say that these groups so defined for negative integers were periodic with period 2 in I, and therefore could be defined by periodicity for all integers, and then they fit into the long exact sequences that give one a cohomology theory. Of course, it's a homotopy functor on the category of compact spaces. Well, so that was the first step. And this was a cohomology theory, and one of the points I want to make is that it resembles the even cohomology of X with integer coefficients. I'm going to come back to that. So it was rather like cohomology theory that was already known. More precisely, this has a grading, and of course the Atiyah-Hirzebruch spectral sequence begins with this and converges to the graded group associated to a filtration of that. I'll come back to that later. The fact that this is in some sense a deformation of this, or vice versa. Well, then, of course, the next observation was Serre's theorem, that if you consider the Banach algebra of continuous complex functions on a compact space, then finitely generated projective modules for this ring, so finitely generated and projectives, these are exactly the same thing as vector bundles on X. And therefore, that suggested that just as you make this out of the category of vector bundles on a space, so when you take any ring A, we can consider the category of finitely generated projective A modules. That has a direct sum. They form a semigroup. One can again adjoin negative elements, and one will have a ring which, for the moment at least, I'll write K naught of A. Well, that was an interesting thing to do, but of course the question immediately arose, can one make that into a cohomology theory in some way analogous to what was done before, because that would obviously make it a much more useful tool. So people ask, can you define groups Ki of A for other I? And the way this was initially done was to say, well, we're trying to make a cohomology theory on the category of rings instead of on the category of spaces. So the natural thing to do is to look for some functors that satisfy long exact sequences. So when you have what you might think of as a Meyer-Vietoris situation in the category of rings. So suppose you have two rings, A1 and A2, which both map. So if you think of these as like the rings of functions, you see these would be the functions on the intersection of the spaces on which these were the two intersections. And so if you have a ring that fits in like this, making a Cartesian diagram, you can think of this as like the functions on a Meyer-Vietoris diagram. So you might hope that the functors that you apply to these situations would fit into a Meyer-Vietoris sequence like what you have in ordinary cohomology. So that was the sort of thing that was done with some measure of success. But then Quillen came on the scene and introduced a complete paradigm shift because he adopted the point of view that what one's trying to do is not define a cohomology theory on the category of rings, but one's trying to associate a cohomology theory to a ring. So he said, let's look again at compact spaces and define a functor Ka naught of x. And how do we do that? Well, we could look at the bundles of finitely generated projective A modules on X. A might be just a discrete ring, so these would be automatically flat bundles, but no matter. So we look at the bundles of finitely generated modules, and then we adjoin negative ones, so not group by group for each successive, not space by space for each space X, but on the level of the whole functor. In other words, one notices that this can be identified with the homotopy classes of maps of X into the space of the category PA. It barely matters if you know what that means for what's going to follow in this lecture, except that a category has a natural space associated to it. And so this is the space, a space made out of the category of finitely generated A modules. And the actual modules can be the bundles of finitely generated projective modules give you maps of X into this space. And we'd like to adjoin negative ones. Well, we introduce a category of virtual modules, so pairs of modules with an obvious relation which identifies the positive and negative parts. We make a new category, we take the space of that category, and we take this definition. So this was Quillen's definition. And it's not really itself the subject of this talk, so I'm not going to say much more about it now. But he took the category, he introduced virtual objects, took the space, and that's the definition. Now, even so, that gives you a definition, and that would enable you to define, for example, the coefficients of this. So Quillen's idea was that Ki of A should be defined as the Ki, or in some reduced sense, of the theory, the coefficients of this theory. Well, I should write it like this: Ki A of a point. In other words, as pi minus I of this space. And you see, while we could define a string of groups with the homotopy groups of this, in order to get this defined in all dimensions, we need, again, some analog of the periodicity, some way of de-looping this space. We need to make this into a spectrum. We need to have a string of spaces which are right Bn. Such that each is the loop space on the one below. If you take the loops on Bn, you get Bn minus 1 of this. And that gives you the data that gives you a cohomology theory rather than just a string of groups defined in negative dimensions. Well, there's a completely different kind of reason why there's a cohomology theory. And the question is, what's the relation between them? Well, clearly what we've done here is somehow associate a space, or actually a homotopy type, to a non-commutative ring. So we're in the terrain of non-commutative geometry. And so part of this talk, one of the things that fascinates me about this question is what we're trying to do when we do non-commutative geometry. I mean, people ask mathematical questions for lots of reasons, like, if I do this for manifolds with boundary, will I get tenure? That was the reason we met yesterday's talk. Well, I want to... So in connection... So why am I interested in non-commutative geometry? So for me, again, the reason isn't the subject of this talk, but for me the reason is that we think geometrically. Nearly all the mathematics we do is somehow based on pictures, and in fact all the way we process the world is geometrical. On the other hand, at the most basic level, physics tends to tell us that the world is somehow presented to us algebraically, so that our notions of space and geometry and so on are probably somehow made out of algebraic inputs. Now, how does that happen? I mean, which is really prior? And that's the kind of question I'm interested in. So I'm very interested in how one associates geometrical things to algebraic objects such as non-commutative rings. But so in the talk by Graeme Segal yesterday, he was trying to do, I think, very much the same kind of thing. But my approach is in a sense more that of a topologist, in that I'm interested in what you might call genuine homotopy types of spaces. So let me just say a word about that. When Kohn originally motivated non-commutative geometry, he was thinking of generalizing the notion of a space. A non-commutative space was some way of having objects which represented things which had space-like properties, like the space of leaves of a ergodic foliation of a torus or something, which nevertheless the ordinary notion of a topological space wouldn't quite capture. Now, so that's generalizing the notion of a space. What do we want from a space? Well, a space, the most obvious thing about it is in a space you have a notion of proximity. You know what it means to move continuously from one point of it to another point. You know when a path is continuous, when a function on the space changes continuously. That's the sort of thing you're mostly interested in. You're mostly interested in local properties. But once you have the category of topological spaces and continuous maps, you can of course pass to the homotopy category, where you identify maps which are homotopic. And when you study the homotopy category of spaces, you're looking at spaces when you're interested in precisely the aspects of them which are not local. What is left of the space when you've disregarded all the local information? It's the way it's globally put together. Well, as soon as you do that, of course, you find a category which has a life of its own. There are lots of objects in the homotopy category which don't come from any very definite point of set, any definite space of set of points which make up the space. One of the spaces that's been, or the homotopy types that's been talked about a lot in this meeting, is the space of manifolds of a certain given dimension. That's a homotopy type. Actually, a slightly more interesting example for my purposes is a space which we can all imagine, at least I feel I imagine as a space, where the points are the isomorphism classes, say, of Riemannian manifolds, but the paths are cobordisms. So we can think of this, if we like, as a simplicial set. That's one technology which will capture it. Think of manifolds, and think of a path in the space of manifolds as being a cobordism from one manifold to the other, and then a cobordism between two cobordisms would be path between the paths and so on. Well, now this isn't a space on which you can put a topology, and yet it's a very well-defined object in the homotopy category. It has a well-defined homotopy type. It's the space, of course, which Tom studied, in terms of his work in the 1950s. We know all about the homotopy type of that space. It's one of the few spaces we really do know all about. But see, one of the things that might give you pause when you think about it is for each dimension D, we can define that way a space of D-dimensional manifolds in which the paths are cobordisms, and the loop space of the space of D-dimensional manifolds will be the space of D plus one-dimensional manifolds, and so on. And of course, the space is defined for positive and negative D. So what's the space of minus 10-dimensional manifolds? Well, if you ask what its points are, it has just one point, the empty minus 10-dimensional manifold, and you don't see anything until you start looking at what its simplexes are in dimension 10, when in order to find something of dimension minus 10, you have to grope around with at least 10-dimensional hands to begin to hit it. But nevertheless, we have this perfectly good homotopy type. And I do definitely want to think that we have these good things, which are homotopy types of honest spaces somehow, even though we're presenting them in a rather abstract way. Well, in fact, I'm going to say something worse, though, because one of the points I'm going to be making is that all you can associate, as far as I can see, to a non-commutative ring is not even a homotopy type, but a stable homotopy type. I'll come to that later. That's something even further away from being anything like an honest space. I'll come back to that later, though. Well, well, actually, perhaps I'll say one thing about it now. I mean, we're going to have things which not only are like spaces of negative dimensional manifolds, but if we're going to introduce the stable homotopy category, we allow ourselves formal D-suspensions, so we can have negative dimensional spaces. And of course, in a certain level, those things have been around for a long time. It was a tremendous step forward, I suppose, in the 1950s, when Serre introduced a new point of view on finding the intersection multiplicities in algebraic geometry in the following way. When you have an algebraic variety, say, which is defined by a ring of functions A, and you have two subvarieties, so think of this as representing some algebraic variety, and you have two subvarieties which are intersecting in some complicated way, which consists of things which have sort of multiplicities, then there'll be an ideal of functions I which vanish on this one and j which vanish on that one. And if you're, like me, educated in 19th century algebraic geometry in Australia, you investigated this intersection by fiddling around with the equations, deforming them a little bit till this intersection sprang apart and looked a bit more like a proper space, and you said that, there was like the roots of equation, there are really 6 points all jammed together there or whatever. So we made some sort of hook or crook interpretation of the intersection. And Serre observed that the way to look at it is to look at the ring of functions on this one and on that one, A mod j, and to take in the Tor groups over the ring of functions on A of the ring of functions on the two varieties. Now, so this is a sequence of abelian groups, and he, of course, defined the intersection multiplicity as its Euler characteristic. But what one's really doing is one's constructing a stable homotopy type, of which this is the minus I, if you think about it. You see, things are upside down because these are the rings of functions on things, so they have the opposite variance to the things themselves. This is the minus I homotopy group of that intersection. So you're thinking of the intersection as something potentially negative dimensional. Of course, that makes good sense in that if you had two things which are of sufficient codimension, you wouldn't expect them to intersect at all. You expect the true intersection to be somehow something negative dimensional. Again, you will only begin to see it when you move things around a bit so that things really do meet. Well, with that prolegomena, let me then talk a little bit about how one, before coming back to Bott periodicity, how do we associate homotopy types to algebraic objects? So supposing we have a ring, what kind of thing, how might we go about getting a homotopy type? Well, of course, when Quillen came into the subject, the big thing in the world was Grothendieck's invention of the étale homotopy type of algebraic varieties. The point is that the homotopy type of a space is something which is incredibly robust. You can find by lots and lots of different methods. You can take the space and define its homotopy type in the obvious way, but on the other hand, you can associate any number of categories to the space such that the space of the category is the homotopy type of the variety. For example, you can take all the contractible open subsets of the space with inclusions, so that's an ordered set. Think of that as a category. Take the space of that category, that's the homotopy type of the variety. Or if you're in reasonable situations, you might consider all spaces mapping into the space, just the category of all spaces over it, and then somehow filter that and take the limit as you consider all sufficiently small spaces. Or you might, there are any number of things of that kind you can do. So Grothendieck's idea was that you could define a category of somehow generalized open subsets of any algebraic variety, and when you considered the space of this category, this was the homotopy type of the variety, even for a variety of a field of characteristic P or whatever. And of course his aim was to use that to prove the Weil conjectures, and he proved some of them, and the program was carried through eventually by Serre. Well, so Quillen was very full of that, and he, about the same time, just before, in fact, he started on algebraic K-theory, he wrote his book, which wasn't famous at the time, has become very famous since, on homotopical algebra, in which he invented model structures and axiomatized homotopy theory. And the reason he did that was because he was interested in defining homology and cohomology groups for commutative rings. And he makes this rather blunt statement at the beginning that he's defining these groups that are clearly the right homology groups according to Grothendieck's principle for the category of commutative rings. And I don't know if anyone pointed this out before, but that was a rather odd thing for him to say, because Grothendieck had established that commutative, and Quillen certainly is constantly alluding to this all through his book, commutative rings are affine varieties. That was Grothendieck's picture. Étale homotopy theory had been just invented for dealing with that. Quillen now applies Grothendieck's techniques and associates a new homotopy type to commutative ring, because he defines as the category of open sets the rings which surject onto the ring he starts with, commutative rings. So he's actually considering infinitesimal thickenings if he's working in the category, in the algebraic category. So he's doing something exactly opposite to what Grothendieck was doing, and producing a completely different homotopy group, homotopy type, which is in some sense dual in the sense of homotopy theory to what Grothendieck had been doing. And it's sort of slightly weird that Quillen, I have no idea what was passing inside Quillen at that stage, because he didn't comment on this at all. But let me just mention a few things, for instance, that are intriguing about commutative rings. If one, I must remember when I started this lecture.
The half past.
I started at half past, yes. So if you start with the ring C of x, the continuous functions on a compact space, we know we have this category of finitely generated projective modules, things I call PA. But of course, you can also consider the category of modules of finite length. Let's call that F of A for the moment. So they would be finite dimensional complex vector spaces with an action of this ring. So this depends covariantly on A. This, if you think about it, depends contravariantly on A. And of course, there's a pairing between these two things, in that if you take a finitely generated projective module and one of these, you can tensor them, and then you can just do the forgetful functor into vector spaces, and you get a pairing from this category across this category into this category. And if you take the spaces of these categories, you do get things which are dual homotopy types with respect to the category of vector spaces, which those of you who are algebraic topologists will know. This will give you the dual with respect to the BU spectrum. So you get these dual things. On the other hand, you can do other things again. One of the other things that was mentioned in yesterday's talks is the Koszul duality. So here we have two, for a commutative ring like this, we have these two opposite categories which we could associate. But we could also take a completely different ring associated to X. We could take imagine this is a connected space with base point, and take the base loop space, omega X. And then let's take the free algebra over the complex numbers generated by that space. Well, if you take the finite length modules over that, then of course by using a connection, you see that there's an equivalence between vector bundles and modules for this. So again, here is the category F for this ring looks like the category P for that ring, and so on. So there are very many games you can play in the case of a commutative ring. In the case of non-commutative ring, of course, this picture generalizes, because if we were doing ordinary algebraic geometry, here we would have the category of vector bundles, here we would have the category of coherent sheaves, and so on, and there are this well-known sort of Poincare duality coming in, which doesn't seem to have any analog in non-commutative geometry. So let me just mention the fact that that's something that we don't have the freedom to do in non-commutative geometry. So let's now come back to Bott periodicity. So Quillen had a favorite proof of, there are many, many proofs of Bott periodicity, and I'm going to mention two of them in this talk. Of course, Bott's original proof was by Morse theory, an incredibly beautiful geometrical proof, but it's not the one I'm going to talk about today. Quillen had his own favorite proof, and it was in terms of this de-looping, which he had become very familiar with for in defining algebraic K-theory. So we have some category C, which is an additive category, which is the category which we're trying to define our homotopy type of. So Quillen observed that if we take a compact space X with base point, we can define a new category. So this is now compact with base point. We can define a category X slash C. We can, so to speak, tensor the category with C. This is actually a topological category. I won't linger over that though. So we have X, and we pick a finite number, so there's a base point somewhere, which we'll call infinity, and we have a finite number of, we imagine having a configuration of a finite number of points in X, so this is X. And attached to each of these, we put a label, which is an object of this category C. And we make that into a space. where we allow the points to come together. So this is with a composition law, which I'll think of as direct sum. You allow these points to come together, and then you just add the things to, when the points coalesce, their labels get added by the direct sum. And this gives you a new category. A morphism from one of these objects to another one is something which it's a collection of morphisms in C where you're only allowed to map labels to things which are labeling the same point. In other words, you think of it as like a direct sum of things indexed by the points of x, and you think of them as sort of graded maps graded by x. Well, so you define this, and you then observe that this is precisely, the space of this category is precisely the desired n-fold d-looping of C, the thing that we wanted up there. And in particular, if we just want to d-loop at once, which is what we want to do at the moment, we'll be interested in n equals 1. So let's now think about the Bott periodicity theorem. Well, Bott, of course, thought of it as like this, that you take the unitary group U infinity, which is the union of all the unitary groups UN, embedded in each other in the obvious way by top left-hand corner of a matrix. And he observed that there was a natural map from this into its second loop space, which is a homotopy equivalence. But Quillen proved this in a slightly different version. So the version which he liked to describe was the one where we relate the unitary group. We want to relate U infinity to B of the category of finite dimensional vector spaces. So that will be equivalent to Bott periodicity if we prove a homotopy equivalence like this. Well, so what is an object here? Well, you see, it's a unitary matrix. We can think of it as a finite size unitary matrix of some large size. So when you have a unitary matrix, it has a spectrum which consists of some points on the unit circle. So this is an indeterminate size matrix, so it will have finite number of eigenvalues which are not 1, and then it will have infinitely many eigenvalues 1. Gosh, I forgot to tell you when I was describing this space how we use the base point. The base point is used because when a point moves to the base point, you discard it in its label. So it's a sink where things are allowed to vanish. So similarly here, these eigenvalues are allowed to get to 1, and then they drop out of the picture. Well, attached to each one of these eigenvalues, zeta say, there's the corresponding eigenspace v zeta. So, and these are orthogonal subspaces contained in this space on which these matrices act. They're all orthogonal. So this is essentially what I described over here, except that the spaces are required to be orthogonal. And if you think about it, if it's an infinite dimensional space, then the finite sets of finite dimensional subspaces which are orthogonal has the same homotopy type as the ones which are not orthogonal, so that makes no difference. So this is exactly a picture of this, and that was the proof of the theorem. So how does one, so that's very topological, of course. Can one somehow produce an algebraic analog of it? Well, you see, supposing you wanted to replace the complex numbers by, let's say, a general algebraically closed field K, then what would change is that these eigenvalues, instead of being points on the circle, which is what we want to put into this construction, would be points of the multiplicative group of the field. So what we seem to have proved, you see, is something that relates B of the category P. Well, we'd be looking at projective modules over the field K. We seem to be saying that this looks somehow like the multiplicative group of the field K smashed with the category PK, whatever that means. Well, of course, but this is an algebraic variety, and in some way we do know about homotopy types of algebraic varieties, and we know that this should in some sense have the homotopy type of a circle, and so in some étale theoretic sense this is a version of Bott periodicity. Let me just digress for a moment here. When one's trying to associate homotopy types to algebraic varieties, one has two basic strategies. One is the one I've already mentioned, the Grothendieck picture, where you introduce some combinatorial, some category, like the category of some kind of generalized open sets, which you can define algebraically, and then you take the space of that category. And that gets you into topological spaces, because taking the space of a category, that's a space. The other approach one has, and the thing that one nowadays associates, I suppose, mostly with Vojevodsky, but of course it was used in lots of versions by lots of people before him, is the sort of way in which you think of the ground field over which your algebraic variety is defined as a sort of honorary line. I mean, although it's just maybe an algebraically closed field of characteristic P, you think of it somehow as a line. So you think of, for instance, being allowed to deform things by simply decreeing that a line is a line, even though it's over a field which has no topology. And that's kind of the situation you have here. So one of the things I want to emphasize is that we started off with a certain category, and we've used these two different ways of moving into topology, one on this side and one on this side. And of course that's very basic in all the Vojevodsky theory, where there are these, in the stable homotopy category of algebraic varieties, you have these two different ways of suspending, one connected with this circle and one, so to speak, connected with that circle, the two different things. And that's one of the reasons, in ways in which this Bott periodicity, I think, does illuminate the sort of way in which we're trying to associate a homotopy type to an algebraic variety. Well, nevertheless, this is still very vague. There are two things I wanted to mention. Well, we want to ask the question, what kind of manifestations of this in purely algebraic situations might one look at? And there were two I had in mind. One was the periodicity which occurs in manifold theory. Those of you who do surgery theory, the fourfold periodicity of the L groups. The fact that the dimension of a manifold is interesting mod 4, because if you have manifolds of dimension divisible by 4, they have a middle dimensional homology group on which there's an intersection form which is a symmetric non-degenerate quadratic form, whereas if the manifold has dimension congruent to 2 mod 4, you have a skew form in the middle dimension. Odd dimensional manifolds don't have a middle dimension at all, obviously, but they have kind of linking properties between the things around the middle dimension. So there's the algebraic statement is that if over, say, a commutative ring, you consider chain complexes of abelian groups, so they're the crudest model for the homotopy types. Or if you like, just consider stable homotopy types, but consider them as having self-duality in dimension n. Think of chain complexes. Perhaps it's easiest to think of chain complexes. Think of chain complexes and think of them as being equipped with duality in dimension n. In other words, you pair things where the dimensions add up to n. and get a non-degenerate pairing between the complexes. Supposing you can make a kind of simulacrum of manifold theory with such things, because you can say what it is for a manifold to be closed. The manifold is non-degenerate, the form is non-degenerate. A degenerate form is like a manifold with boundary. When you have such a thing, the mapping cone of the thing into its dual, given by the quadratic form, is the boundary of the manifold, you see, would be contractible if the form was non-degenerate and so on. So one can make a category, a homotopy category out of chain complexes, and clearly it's periodic of period 4 with respect to dimension. Well, Karoubi pointed out the way that is related to ordinary Bott periodicity. I'll come back to that in a second. But before that, I'll say one other thing, which I'll actually have to say very, very quickly. And that is the related really to a different proof of Bott periodicity. The other manifestation of Bott periodicity, which has been talked about to some extent at this meeting, and is also one of its most basic manifestations, is the S operator, Con's S operator in cyclic homology. The fact that it's first proved by Goodwillie, but then there's a more explicit and more perhaps illuminating proof by Ezra Getzler of the fact that when you have a non-commutative ring, it has cyclic homology, and that is only homotopy invariant when you invert an operator called the S operator, which is closely related to Bott periodicity. Now, I'm not going to really have time to go into that, so I'll just say something rather tangential about it, which brings me back to what I said right at the beginning about how K-theory is a deformation of classical cohomology. So, again, this will be very well known to a lot of people, and I'll say it very basically. Let's begin. There's a very well-known way which goes back into the mists of time, like the 19th century or something, at how when one has an abelian group which is filtered. So supposing we have and supposing this can be a positive or negative integer. Well, let's begin with a really simple case. Imagine this thing is a finite dimensional complex vector space, and so this is really just, although I'm grading it by z, for sufficiently large k we're just got e, and for sufficiently small k we've got 0. There are only finitely many steps. Then, of course, it's well known that you can think of E as a deformation of the associated graded. Call that GUR E. You can think of this as a deformation of this in a well-known way. Let me just say very quickly how that goes. Well, you introduce something which was called the Rees module, I suppose, of E, of the filtration. So I'll call that curly E. This is the direct sum of, let's say, I'll take a formal indeterminate. Think of that as contained in E with an indeterminate T adjoint. And this, of course, is a module over the polynomial ring Ct, which just multiplies by T with respect to that formal variable. Well, so the thing about this Rees module, it's a finitely generated projective module over that ring. So it's the module of sections of an ordinary complex vector bundle, which I'll write lots of E's in this. So this is a complex vector bundle on the complex line. This is a complex line parametrized by T. That's true of, that's Serre's theorem about relation between vector bundles and projective modules, but if you like, the fiber of E at T is just E fiber at zeta is E modulo T minus zeta E. You see, so the fiber at 0 is E modulo TE, which is obviously the graded group associated to E, and the fiber at 1 is exactly E. Well, so in what sense is K-theory? And there's a converse to this. When we have a complex vector bundle on the complex line, this one has the obvious extra property of being an equivariant vector bundle with respect to the multiplication action of C multiplicative on itself, because the fact that this is graded says that if we multiply, let C multiplicative act by zeta multiplying by zeta to the k on the kth term, that will be a C multiplicative action on this, covering the natural action on there. And when you have such a C multiplicative equivariant vector bundle on C, that's exactly equivalent to giving a graded module whose and it's exactly equivalent to giving a filtered vector space E and an associated vector bundle which interpolates between the graded and the filtered. So how do we see this as a way of interpolating between K-theory and cohomology? Well, again, this is pretty obvious, I guess. But I'm again emphasizing it because, you see, this is going to be a purely algebraic deformation. The space which represents cohomology is a product of Eilenberg-MacLane spaces. It's absolutely not homotopy equivalent to the space which represents K-theory. So we're not going to get a family over any kind of my idea of a line, which is going to be one thing at one point and the other thing at the other point. Nevertheless, algebraically, it's a good deformation. In fact, the deformation is exactly Bott periodicity. We have this space of vector spaces, the thing that represents K-theory, Z cross du, or I should do that before it. I suppose I better write virtual vector spaces. Well, we have an obvious map from S2 smash this into this. Well, you see, what do I mean by say? You see, if I think of K-theory as being the spectrum which emanates from this space of virtual vector spaces, I'd like to somehow, I said it was filtered, K-theory was filtered, but I'd like to somehow set up this structure. Well, the obvious thing we have is the Bott map, like this, which tells us this sits inside CP infinity, which is the space of complex lines, and this is complex lines, this is vector spaces, and this operation is just cancelling a line with a vector space. And in fact, we have this map like this. I won't keep writing virtual. And of course, we're in this category of spectra, which are somehow modules over the sphere spectrum. So if I think of I can't just, if I want to take the free algebra generated by this space in the category of spectra, I have to take the sphere spectrum smashed with CP infinity, or perhaps I should write it like that, or perhaps you'd like to write it Q CP infinity plus lots of ways of writing it. Anyway, you get this and this is like the action, well, so this is like, in this stable homotopy category, this is like the polynomial ring in one variable, except that the variable has degree 2, it's doubly suspended. And the relation between the Bott way of defining K-theory and the Quillen degrouping is that these Quillen D-loopings, these connective ones, sit inside, so perhaps I'll just go back to this picture. Each of these things is exactly the same. They're each the Quillen K-theory spectrum for K-theory. Each of these things is just this virtual vector space of complex vector spaces. At each of the maps is this wedging with vector bundles. This is the analog of this is this, and so on. And when we want to take the fiber at t equals 1, oh dear, I did something. No, I think I've done it right. So we have made this formal family of spectra over the sort of line which is somehow represented by that, and used that to interpolate between K-theory and cohomology. I've said that in a slightly muddled way, and I think I'll only get more muddled if I try to say it again. I tried to say it a little bit too quickly and said it a little bit wrong. So I'm not going to, I have very, so I wanted to mention another proof of Bott periodicity, which sees it as a deformation. And this is the proof which I always associated with Kohn, although it's maybe perhaps really due to Kuntz. I'm not really completely sure. But again, it goes back in many ways. Supposing we start with so we're thinking about non-commutative geometry. Supposing we consider the C-infinity complex valued functions on the plane and take the ones which vanish rapidly with all their derivatives at infinity. So I'm really thinking of the Schwartz space of rapidly decreasing functions. So this is the space which in the dictionary between algebra and geometry represents the two-sphere regarded as a space with base point. Well, it's well known that geometric quantization gives you a one-parameter deformation of this to the space I'll call smoothing operators on L2 of the line. In other words, essentially, so you can just literally introduce a parameter, Planck's constant, define a deformed multiplication on this, which when h is naught is the usual pointwise multiplication, and when h is positive, well, the isomorphism class doesn't change as soon as h is non-zero, and the thing becomes the operator of kernels on the line, smooth kernels on the line decaying at infinity, so operators which acts on the Hilbert space of functions on the line in the usual way. And this is a full matrix algebra, so the finitely generated projective modules for this are simply equivalent to the category of finite dimensional vector spaces. On the other hand, the category of finitely generated projective modules for this is the category of vector bundles on the two-sphere pinned at the point. And of course, if we now take this with coefficients in any other ring, which we can do, we'll get an equivalence between the category of finitely generated projective A modules and the same thing doubly suspended. So if we're going to make any assignment of homotopy type to a ring, which is going to be invariant under this kind of algebraic deformation, which after all is what we would somehow expect, then it's going to you're not going to be able to tell the difference between a space and its double suspension. You're going to be forced to identify double suspensions. Now, this identification is yet another proof of Bott periodicity, of course, and that relates to the deformation argument I just gave not in a way that I don't really have time to explain. So I'm going to spend then 3 minutes telling you what was going to be, I meant to spend a bit more time on, alas. This question of how Bott periodicity relates to the periodicity in manifold theory. So this was in some sense explained by Karoubi in a famous paper in the Annals in 1980, where he talked about the K-theory for the orthogonal group over a general commutative ring and produced a version of Bott periodicity. Now remember, I said the periodicity we're interested in is the periodicity of complexes of abelian of A modules for a commutative ring and cobordisms of maps in the algebraic sense. What that amounts to is you're looking on the one hand at the category of finitely generated projective modules with quadratic form, and the fact that you're interested in them only up to cobordism means that you want to kill the ones which are boundaries. So from the original category, these are A modules, we have a functor like that, which is the hyperbolic functor, which takes a module to the module plus its dual, which you can do for a finitely generated A module. And that's the thing which puts the manifold with boundary inside the boundary. And we're interested in the cofiber of this. And this theory is the thing which is meant to be fourfold periodic. So Karoubi observed that the Bott argument works fine here. So how did he do that? Well, looks like I don't have time to tell you this properly, but there are I know at least 3 other ways of defining de-loopings in this of this kind of category. And they differ only a tiny little bit from each other. They go in imperceptible steps. But some are more convincing. I'm afraid I've really timed this talk very badly, so I don't have time to tell you this beautiful story. But the other 3 methods, after the Quillen one, although they're only imperceptibly different, so to speak, they produce non-connective de-looping. In fact, in a certain sense, they were known before Quillen, in that they were used to define ki for negative I before the whole Quillen story got going. And they agree with each other. And what's more, they make sense for rings with topology and so on. So you can apply them to the usual complex numbers. And when you do that with topology, apply it to the complex numbers, you get the usual Bott periodic de-looping. So you can also use these 3 methods, which I'm terribly sorry I don't have time to tell you, on this category. Well, what Karoubi essentially observed was that you can get Bott periodicity in this picture in the most obvious way, because you can define, with respect to, say, the rational numbers as your ground field, an element in dimension 2 and an element in dimension -2, which multiply not quite to 1, but actually to 4. So there's a problem if you do it in the most straightforward way. You're only getting periodicity away from the prime 2. So he just wrote down the usual Bott things there. Now, this is much more peculiar than it looks, because the de-loopings in question somehow, as I say, there was this sort of homotopy between plausibility and things that seem completely wrong way round, which I was hoping to have time to explain to you. The thing in dimension -2, that, you see, you wouldn't be able to see on the orthogonal, on the general linear group in ordinary K-theory, because the Quillen theory is automatically connected. So how does that happen? Well, it's because if you represent a two-sphere or something as a two-sphere, it doesn't have any interesting ring of functions. Nothing happens to, there's no element there. But curiously this fact that the connectivity that occurs in Quillen theory doesn't apply in this orthogonal case, and so you extract this. Well, I'm over time, so I really better stop, and I shan't tell you any more about that story. So that's it.
Thank you very much. Are there any questions? Okay.
Good. So what was it? You made a remark about how the atal homotopy type of a ring related to some K-theory space of its Kazul dual. Could you say that again, or say it?
So what was it?
You said that I believe you said that the atal homotopy type of a ring had some relation to the K-theory space of its Kazul dual. Did you say that? And you gave the example of the loop space, the like cochains on the space versus chains on the loop space, or something that functions on the space versus C of the loop space.
Are you thinking of what I said about finite length modules over the algebra of the base group? Sorry, I'm not sure.
That was where he said it.
Sorry, I'm not taking.
Oh, so I thought that you said. I'm sorry if I misunderstood. That the Quillen story was dual to Grothendieck's, and that.
Yes. Sorry. Well, I mean, on one sense, all I was meaning to say was Quillen, when he's defining the homology for a commutative ring, so he's not talking about non-commutative rings. He said what we have to do is say what a covering, what a generalized open set, define a Grothendieck topology on the category of rings. And what he does is he considers rings which surject onto the rings he started with, and maybe have certain properties. But you see, in algebraic geometry, that's an infinitesimal, that's a thickening of the ring. You see, so he was exactly considering the dual pattern. But is that what you were?
Yeah. Yes.
So he's completely, he's just reversing the variance without comment.
Okay, that's an answer. I was just wondering if there was. So what I took away was maybe that there was something more to say about the atal homotopy type on the one hand versus the K-theory homotopy.
I don't know that. No, I'm sure there is actually, but I certainly can't say it this minute. Sorry, did someone else have a question?
Are there any more questions?
Yeah.
Okay. There is a striking analogy between say geometric Bott periodicity and the periodicity of Clifford algebras, and I think that Karoubi has some kind also of proof where he proves Bott periodicity, or Atiyah perhaps by means of Clifford algebras. Is there a simple way of understanding why this works?
Well, because that's an earlier aspect. That's 20 years earlier, Karoubi. So the Clifford algebras, of course, are periodic, and Karoubi. That was more a way of, you see, Bott periodicity for the complex numbers is periodicity with period 2, and there you're simply going alternately between the unitary group and the Grassmannian, which you can think of as the projections and the self-adjoint projectors in the unitary group. So you can do the whole story over the complex numbers simply by working with things which are mod 2 graded and things which are ungraded, and observing that if you grade twice, you'll then have the 2 by 2 matrices over what you started with. That's the periodicity of Clifford algebras. And so in some sense that's more just how you keep track of the formalism. the Clifford algebras really only became important when one was doing Bott periodicity over the real numbers, where there are 8 steps. And then, of course, you need some real technology to organize how things take 8 times to get back to where you started off with. But that's sort of to do with the Galois descent between grading and complex conjugation and the different ways they interplay. I think though that was historically very important, but maybe not so really fundamental as it was more, I think, bookkeeping on a certain level. It was a way of keeping track of Bott periodicity in the real case.
Any more questions? Okay, we'll thank the speaker again.